In this brief talk, we concisely overview the learnt harmonic mean estimator that we proposed recently for Bayesian model comparison. You can find further details in the paper, which is available on the archive, and also access the code implementing the estimator on GitHub or through PyPy. To set the notation, consider Bayes' theorem, where the posterior is related to the likelihood, prior, and model evidence, or marginal likelihood, as follows for parameters theta, model m, and data y. Throughout, we adopt the following shorthand notation. For Bayesian model selection, we're often interested in the model posterior odds, which are related to the Bayes factors of the different models via the prior odds. We must therefore compute the Bayesian model evidence, also called the marginal likelihood, for a given model. This involves computing a multi-dimensional integral, and so is an extremely challenging computational problem in higher dimensional settings. In this talk, we focus on harmonic mean estimators for computing the evidence, or marginal likelihood. The original harmonic mean estimator was proposed in 1994 and relies on the following relationship. Consider the expected value under the posterior of the reciprocal of the likelihood. Expanding and substituting the posterior, it is straightforward to show that this term reduces to the reciprocal of the evidence. This relationship suggests the following estimator, where the evidence is given by the harmonic mean of the likelihood given samples of the posterior. However, it was realized almost immediately that the original harmonic mean estimator can fail catastrophically. To see why the original harmonic mean estimator can fail, let's consider an alternative importance sampling interpretation. We can write the previous relationship as follows, which we can interpret as importance sampling, where the prior plays the role of the sampling target distribution and the posterior plays the role of the importance sampling density. For importance sampling to be effective, we usually ensure the sampling density has fatter tails than the target distribution. However, this is not the case here, since the prior, which plays the role of the target, is typically broader than the posterior. It is therefore not surprising that the original estimator can fail catastrophically. To address this issue, what we've called the retargeted harmonic mean estimator has been considered, where an alternative importance sampling target, phi, is introduced. Again, expanding and substituting the posterior, we recover the reciprocal of the evidence. This suggests the following estimator. By an importance sampling interpretation again, we see that phi now plays the role of the importance sampling target distribution. We can therefore recover a well-behaved estimator by ensuring the importance sampling target phi does not have fatter tails than the posterior. But the question remains, how do we set the target distribution phi in practice? A variety of approaches have been considered, for example Gaussians and indicator functions, but none have proved completely satisfactory. Typically, a Gaussian has tails that are too broad, capturing regions of the parameter space where the posterior is very low, while indicator functions are too narrow for complex distributions, resulting in inefficient estimators. We can obtain intuition regarding effective targets by considering the optimal target distribution, which is simply the posterior itself. However, the target must be normalized, so the optimal estimator is clearly not feasible in practice since it requires knowledge of the model evidence, which is precisely the term we are attempting to estimate. We recently proposed the learnt harmonic mean estimator, where we learn an approximation of the optimal target distribution. The approximation itself need not be highly accurate, but critically, it must not have fatter tails than the posterior. Essentially, we learn a target by fitting a model to minimize the variance of the resulting estimator while ensuring it is unbiased and with possible regularization. We solve this optimization problem with a bespoke mini-batch stochastic gradient descent algorithm and develop strategies to estimate the error of the estimator and other sanity checks. We advocate cross-validation to select models and hyperparameters. Please see the paper for further details. We consider just one example in this talk, a normal gamma model commonly considered as a benchmark problem for comparing techniques to compute the model evidence. The harmonic mean estimator was previously shown to fail catastrophically for this example, where the computed evidence was essentially insensitive to changes in the size of the prior. A nice property of this model is that its evidence can be computed analytically for comparison with estimates computed numerically. In this plot, we show the ratio of the evidence computed by our learned harmonic mean estimator to the analytic value. We clearly see that the evidence estimates are accurate and, in contrast to the original harmonic mean estimator, are indeed sensitive to changing prior size. Comparing the evidence values computed by our learned harmonic mean estimator with the original estimator, we see that we improve the accuracy of the estimator by around 4 orders of magnitude in log space. Please see the paper for further examples. In all cases, we find our learned harmonic mean estimator to be accurate and robust. We have developed an open source software code implementing the learned harmonic mean estimator, where we have paid careful attention to the design, implementation, and documentation of the code, following software engineering best practices. The code is available on GitHub or can simply be pip installed from PyPy. In summary, we have proposed the learned harmonic mean estimator for computing the Bayesian model evidence, or marginal likelihood, for Bayesian model comparison. The estimator is agnostic to sampling strategy, requiring only posterior samples, and so can be used with any MCMC sampling technique. In a sense, given posterior samples for parameter inference, one can compute the model evidence almost for free. And we've released a professional code that we hope is easy to use. Please see the paper on the archive for further details, or to apply the estimator, see the code and documentation on GitHub. We hope it's useful for tackling your own problems.